Hello, we are Group 7 and we are presenting our materials project for the Construction Technology and Materials 1 course. I'm Ruben Jean.
I am Jen Kaman. I'm New Chen Yan.
I'm Yun Man.
I'm Zhang Yu To.
I'm Brandon Hunter.
The materials that we are going to examine are concrete and timber. Concrete and timber have been widely used as construction materials in the construction industry, and their properties, behaviors, and environmental performance are the important factors which affect their applications. So in our project, our objectives are to investigate the properties, behaviors, and environmental performance of these two materials, and we also aim at examining these two materials by comparing and contrasting their properties, behaviors, and environmental performance. Our project is divided into 5 main sections. In the first section, the microstructure properties of concrete and timber will be examined respectively, and comparison and contrast will be made between them. In the second section, the thermal properties of concrete and timber will be examined respectively, and comparison and contrast will be made between them. In the third section, the AAR or ASR of concrete and the influence of insects and worms on timber will be examined, and comparison and contrast will be made between them. In the fourth section, the professional practices for testing the thermal conductivity of concrete and timber will be discussed. Lastly, a conclusion will be drawn. So let me first talk about the microstructure of concrete. To examine the microstructural features of concrete, I'll focus on the spaces in concrete, the unhydrated cement remnants, and also the hydration in concrete. Regarding the spaces in concrete, there are interfacial transition zones in concrete, and the interfacial transition zones are the weaker regions, and in these regions there is a higher porosity and also a high water to cement ratio. And we can see that from this picture, the shorter the distance between the cement paste and the aggregate particles, the higher the porosity, and therefore the weaker the cement paste. And actually these are the interfacial transition zones. Actually, if we want to pack the cement grains in a more densely way to the aggregate surface, we can add silica film, and the small silica film will fill the low packing space. And for the porous area and the dense area, we can see that there is a sharp boundary, and we can see a sharp boundary between them. Spaces in concrete. Other than the ITZ, there are some air voids in concrete, and the function of the air voids is to protect the concrete from damage when concrete is exposed to the freeze-thaw conditions. Actually, the air voids usually occupy about 15% of the non-aggregate space. And when we see the air void under the SEM, we can see some of its microstructural features. For example, the air void is not perfectly spherical, and also there are some holes and lines on the air void. And some scientists suggest that the lines are the thin crystals which had penetrated the air void, and they always appear to be straight lines or showing branching. And these photos show the morphologies around the air void after hydration, as the shell of the air void is mainly made of cement grains. So when the silica film is added to the concrete, and then the silica film particles will react with the cement grains, and then calcium hydroxide will be formed, and therefore there will be an internal deposit of calcium hydroxide in the air void. Unhydrated cement remnants. The clinker components include these 4 compounds with some minor components, and the components are actually crystals, and their sizes range from 1 millimeter to 60 millimeters. And for the clinkers, their sizes range from 2 millimeters to 80 millimeters. Generally, individual crystals will not be separated during the grinding process. Instead, the clinker mass will be broken down as a whole. Therefore, after the grinding process, the fragments of the crystals of different types of crystals will probably be found in each clinker. And after a full completion of hydration, a hydration shells will probably be found to be surrounding the remnants. Hydration in concrete. There are two products in hydration in concrete, and they are CSH and calcium hydroxide. CSH is the hydration of these two compounds, and it is composed of silica, calcium, and water, and it usually exists as the hydration shell. However, it is not a must that the hydration shells will be generated. For example, in this picture, for the cement grades A, there is a hydration shell, but for B and C, they do not have the hydration shells. And for calcium hydroxide, it is only a product of the hydration of cement, and it usually exists in irregular marks.
Microstructure properties. Timber. Timber can be divided into two types. One is the hardwood and the other one is the softwood. Hardwood has broad leaf, while the softwood has needle-like leaf. Therefore, the classification of the timbers is not dependent on the relative hardness or density. For example, some hardwood, such as basswood, is softer than the softwood, while some softwood, such as Douglas fir, is harder than the hardwood. Therefore, we can see the difference between the hardwood and the softwood. 4 major cell types. Timber is formed by 4 major cell types, which are trachea, vessel, parenchyma, and fibers. Firstly, I will introduce trachea for you. Trachea is a long cell, and it is about 1 to 10 mm long. They serve as a conductive and mechanical support to the timbers, and you can see the pictures. It is a transverse section of the trachea, and it is as a square shape of the trachea. And the second one is vessel. It is about 0.05 to 0.2 mm long, and it is a water conducting cell for the timber. The size of the vessel is much smaller than the trachea, and here is the picture of the vessels. You can see that there is a large opening of the vessel. Fibers is an important cell type for the timber because it will provide mechanical support to the timber, and the size of the fibers is about 0.2 to 1.2 mm long, which is longer than the vessels but shorter than the trachea. And the last one is the parenchyma. It is present in the softwood and the hardwood, and the size of the parenchyma is also 0.2 to 1.2 mm long, and the size in the softwood and hardwood are almost the same, and also they have the function for storage. Dimensional change. Moisture. Firstly, I will introduce two concepts of the moisture. The first one is the moisture content. According to the definitions, moisture content is the percentage of the oven dry weight, and the moisture content can be divided into two types. One is hygroscopic, and the other one is the free. For the hygroscopic content, the definition is that hygroscopic present inside the cell fibers, but the free moisture content present outside the cell wall. And you can see the difference between these two types of moisture content. And the second concept is the fiber saturation point, FSP. It is the moisture content of the cell wall. If the moisture content of the cell wall is below to FSP, the cell wall will become lost its moisture, and the shape of the cell wall will become strained, and the strength of the cell wall is depends on several factors, such as the specific gravities, the rate of drying, and temperature. The rate of changing moisture content is depends on the external environments, such as the temperatures or relative humidity. In this graph, you can see that the higher temperature, the lower moisture content. When the moisture content is low, the volume of the timber will shrink, and this will affect the dimensional of the timber.
The microstructure of concrete and timber are different in terms of the equipment used for examination, the components, the density, and the function of water. For concrete, the equipment used for examination is backscatter mode scanning electron microscope. And for components, concrete have unhydrated cement remnants, CSH, calcium hydroxide, Haley grains, etc. And for density, the density of concrete varies from place to place. And the function of water in concrete is called hydration.
For the timber, it is common to use optic microscope to examine its cells. Also, we will use the X-ray diffraction analysis to determine the chemical component in the timber. For the components, there is 4 types to compose the timber, which is parenchyma, trachea, fibers, and vessels. For the density, timber also is various from place to place. It depends on the moisture content and the substrate in the timber. Lastly, the function of the water in timber is changing the dimensional of the volume.
Thermal properties of concrete. Concrete's thermal properties and implications vary under the different stages of concrete production. You start out with mixing, which will have thermal effects on workability and slump loss, and then talk about slump loss prevention. After mixing the concrete, you place and cure it. During the placement and curing stages, the main concern is thermal cracking and how to prevent thermal cracking. And lastly, when you have hardened concrete, there are separate thermal properties and implications that are in play, such as thermal conductivity, as well as fire and extreme temperature effects. So let's first look at concrete batching and mixing and the effects on workability and slump. Slump, well, first, workability is the ease of handling concrete during construction, and it's measured through the slump test. And you can see in the figure where an example of a concrete slump test is being done. How does temperature affect that workability? Well, an increase in temperature during mixing increases the rate of hydration and evaporation, which is taking away water from the mix, leading to a loss of workability or a slump loss. And you can see in the figure that as the temperature is higher, that your slump is being lost even more. Some remedies for slump loss include introducing a fly ash admixture to your concrete mix during the mixing stage. And another thermal effect to look at would be cold weather mixing. There's no substantial workability issues, however, this poses the risk of concrete freezing throughout that mixing stage. So some remedies for cold weather mixing include introducing special admixtures to the mix or even heating the water that you're using in that concrete mix. Concrete placement and curing, thermal cracking. Concrete placement and curing. The main concern during this stage of concrete production would be thermal cracking in regards to the thermal properties. Thermal cracking is a phenomenon that occurs due to temperature differences within the concrete structure. So the surface is contracting, however, it's being restrained by a slower contracting going on in the inside of the concrete. And you can see that in a predicted concrete thermal gradient figure where in these different cross sections you have the heat concentrated towards the middle of that concrete structure. With that, you have the risk of compromising the structural stability of whatever structure you are putting together with that concrete. Some prevention methods would be temperature monitoring. Just having a plan in the pre-construction stage of how you will monitor the temperature of the concrete as it's being placed. Admixtures, of course, during the design stage of the concrete can play a role. Pre-cooling and concrete layering, laying down more layers of concrete so that you don't have a massive concrete buildup, which increases that heat differential. Here you can see an example of pre-cooling where in some cases liquid nitrogen will actually be used to pre-cool that concrete. Hardened concrete, thermal conductivity. In hardened concrete, one very important thermal property is the thermal conductivity. Thermal conductivity is really just the quantity of the ability of a material to conduct heat, of how much heat can go through this material. So, should engineers design for concrete with high or low thermal conductivity? Well, it depends. In one case, you will want low thermal conductivity when you want insulation. For example, in a house or anywhere that people are working, you don't want too much heat to be able to easily pass through your blocks or the outer structure of that structure. However, in another case, you may want high thermal conductivity where this structure does not encounter as many temperature differentials, an example of a bridge. And here you can see Vortex, a company advertising their low thermal conductivity, thermally conductive concrete, and how they say that they can significantly decrease the amount of heat that's able to pass through their concrete. Another important thermal property of hardened concrete would be what happens during extreme heat events and those effects. So some effects of extreme heat include decreased strength as well as decreased modulus of elasticity in the concrete. And these are two very important measures in the overall design of a concrete. You want it to be strong, you want it to have a high Young's modulus as well. In case of fire, there's also spalling. Spalling of concrete is when the temperature is getting really, really high and pieces of the concrete are actually breaking off of that structure. Thermal expansion is one last part, which is very important since this is what leads to structural failure. Because concrete does not actually burn, but instead, when it expands, that steel, if it's a reinforced concrete, also expands, and that's where you have joint mishaps and of course the pressures building up and things collapsing and structural failure.
Okay, thank you, Ruben. And now I would like to talk about the thermal properties of timber. Unlike concrete, timber cannot release heat standing by itself during mixing process. Therefore, I would like to draw more attention on how property changed in timber in the thermal conditions. Thermal modification is commonly used by the timber industry. This is to try to improve its dimensional stability, means the strength of timber and resistance to decay. The temperature normally set between 118 degrees Celsius and 216 degrees Celsius. And we can all obtain an obvious change in color and mass rate. The most important thing for thermal modification is to try to control the quality of the modified timber, because the quality are always affected by the temperature, time, and humidity. If these kinds of variables are not controlled in a suitable way, we will face a problem of a serious and unacceptable degradations of timber. First of all, I would like to talk about the strength of timber. We can see that here in this diagram, you can see the effects of time, temperature, and humidity will decrease or increase the strength of timber. First of all, I would like to discuss the modulus of elasticity. The modulus of elasticity means the tendency of timber to it deformed elasticity. It always increases initially in both dry and wet condition. You can see the MOE is over 100% both in the dry and wet conditions. And for the temperature, you can see it's all increased initially from 115 degrees Celsius to 175 degrees Celsius. However, the MOE will decrease when the time is longer and the temperature is higher. And you can see a higher decrease in MOE in the temperature, which is 175 degrees Celsius. And the next one is the modulus of rupture. Due to the high temperature, the fiber equilibrium stress is reducing. Therefore, the resistance to bending will be reduced. And overall, the modulus of rupture will be decreased in both wet and dry conditions. And the third one is the crystallinity. Crystallinity means the degree of the structural order in a solid. If the crystallinity increases, it will increase the hardness of timber too. However, it is not clear under the effect of time, temperature, and humidity. It is because the crystallinity is determined by the increase in the relative width of crystal. And in this figure, you can see if the relative width of crystal is increased, the relative crystallinity is increasing also. However, if the relative width of crystal decrease, the relative crystallinity decrease. And then I would like to talk about the color change under the heating treatment. Color always turns darker with high temperature. In this figure, you can see the one in 220 degrees Celsius is darker than the one in 120 degrees Celsius. However, the color change is only temporary because the color will turn lighter or darker after exposure in outdoor for a long period of time. This is due to the chemical change inside the cell wall of the timber. And the final one, I would like to talk about the mass weight. Mass weight will always decrease with high temperature, and you can see the mass weight will decrease seriously with a more higher temperature. It's because water will be evaporated during the heating process, and also the extractive will be volatile. When the surface extractive volatile are evaporated, the extractive inside the timber will then move nearly to the surface, and this causes more extra mass weight loss.
Thank you, Bobo. And now we will do our thermal properties comparison. One of the first categories or properties to compare will be the strength and how it's affected by temperatures. While in concrete, an increase in temperature during the curing stage will actually show benefits of early strength. However, in the long run, as the concrete after it's cured and as it hardened in concrete, increase in high temperatures will actually decrease the strength.
With timber, it's just like concrete. The strength of timber will increase initially, which is affected by the temperature, time, and humidity. But overall, it will decrease the strength because it's quite difficult for us to control the variables and makes them to be ideal to increase strength rather than decrease the strength.
Next category will be exposure to fire and extreme heat, as well as thermal resistance between our two materials. In concrete, you must first understand that concrete does not burn. However, thermal expansion can result in structural failure when exposed to extreme temperatures in the case of a fire. And in regards to thermal resistance can be designed for in the concrete mix, whether it's with an admixture or how the engineer is designing that concrete mix.
Timber have to burn. However, the thermal resistance of timber is determined by itself, which is the release of char. Releasing char can slow down the heat flow. In a structural building, a large dimension timber can still carry loading because the heat flow is slowed down by the char, and this helps them try to prevent from losing a high mass weight, and this helps the timber to resist loading.
The third category is mass loss. Mass loss in hardened concrete does not occur when in extreme heat.
However, the water content in timber will be evaporated during the heating, and it will decrease the more in a higher temperature.
Interesting. And lastly, we'll compare and contrast the color. Some concretes, if they have limestone aggregates or other types of aggregates, will show a change in color with a temperature rise.
Yeah, timber also changes its color, and it's turned darker normally in a higher temperature, but it's only temporary. The permanent color change will be affected by its organic compound in the cell wall, but not the heating treatment.
So now I would like to talk about the environmental performance of concrete. In our project, we are focusing on one of the most common reactions that's affecting the concrete structure, which is the alkali aggregate reaction, AAR. And this reaction is defined as the alkali in cement react with the aggregates, for example, the silicate or carbonates. But actually, silicate in aggregates is the most common reactant in this reaction. So AAR is usually referred to the alkali silicate reaction. So here you can see is the chemical equation of the ASR, which is the silicate, alkali, and water react together and form an alkali silicate gel. And also you can see in this figure, the silicate gel will form a positive charge on the surface of the gel, and then this positive charge will attract the water contents on the surface. And actually, after the formation of alkali silicate gel, this gel will attract the water content, and when the water content enters this gel, the gel volume will increase. So how can we recognize this reaction? First of all, here are three symptoms that we can recognize this reaction. First of all is the presence of white alkali silicate gel, as this silicate gel is the only product of this reaction. And after the formation of this gel, the gel will leak into the microcrust inside the concrete, and then it will leak out of the concrete structure. So if you can see, this white alkali silicate gel is represent the occurrence of ASR inside the concrete. And second, because of the silicate gel form and also the gel will absorb water and surrounding, it will cause an expansion to the concrete. And after a period of time when the concrete structure cannot afford this a certain extent of expansion, it will cause map cracking on the surface of the structure. And actually, different kinds of crackings represent different kinds of problem inside the concrete. So for the map cracking, is specifically represent the ASR occurrence. So for the protection measures for new concrete construction, the aggregate used in the concrete mixing should be used some non-reactive aggregates such as quartz and marbles. For the cement, we should replace the normal cement by the low alkali protein cement. As you see in this figure, the use of low alkali protein cement could reduce the expansion of the concrete structure by half. For the existing concrete structure, a petrographic examination should be carried out by using a polarizing microscope to measure the potential alkali silicate reactivity, and also the crust should be monitored by regularly for about every 6 months once monitoring assessment, and also if there are any losing concrete, in other words, if there are any spoiling occur, the losses concrete should be replaced by new concrete. And if the situation of cracks and also the spoiling is very serious, popping and also reconstruction to the structure or building should be considered.
I'm going to talk about the cause of insects and worms on timber. However, to better understand this cause, we have to better understand the insects and bugs that cause the deterioration. The two most common bugs or insects that cause infestation and weaken the strength of timber are timber beetles and termites. Timber beetles, they use the protein, they need the protein in the timber for nourishment, and they use the water that's in the timber to digest that protein. And because there is such a low moisture content within the timber that's used in construction, they must eat a lot of it. And that's why they're able to tear down structures so quickly. In the behavior of the timber beetle, when it's in its larva stage, it burrows deep inside the timber and stays there for its entire larva stage of its life, which can last up to 2 to 5 years. Termites, they need the cellulose from timber and other wood products. And what's unique about termites is that they have single-cell organisms called prosans that produce cellulase, which break down the sugars in cellulose for their nourishment. And they tend to feed on the interior as well as the exterior of timber members within structures. And they usually work their way from the bottom to the top of a structure. But sometimes some species of termites are able to colonize in various places of a structure, allowing them to attack such structure from various points. And here are some of the symptoms of insect and bug infestation. To the far left, you see a picture of termite mud tubes. And these are created by termites by the timber within the structure, other wood products, as well as the soil for subterranean termites. These mud tubes are used as transportation ways for them to move throughout structures efficiently. Now, what's typically done to detect whether a colony is active or not is to disturb the tube so you can find the termites are not within them. But sometimes, even when a tube is disturbed and termites are not found within them, it cannot be assumed that the colony is currently inactive, due to the fact that termites often abandon tubes to create new tubes and oftentimes go back to those original tubes for future use. Here's an example, also a symptom of termite infestation, of a pile of discarded wings. Now, these discarded wings are from special swarmer termites. Within a termite colony, there are various roles, such as the soldiers, the workers, and the swarmers. The swarmers are responsible for venturing out from the colony and seeking new land, so to speak, whether that's new timber or a structure that creates a lot of timber members that is very suitable for new colonization. And so if you ever see a pile of discarded wings, it's a very good sign that the structure has begun the infestation of termites. Here to the far right is an example of timber beetle dust. Like I said before, when the timber beetle is in the larva stage, they burrow deep inside the timber, oftentimes from 2 to 5 years. And that burrowing, they dig out some of the timber, leaving behind really fine dust, as you can see in this picture. And so likewise with the termite swarmer wings, if small dust or debris is found on the ground, is a very good indication that you have infestation of timber beetles. And here are some of the methods commonly used to prevent the infestation of insects and bugs. In the top left-hand corner, you'll see an example of a gating system. And this method is used to prevent termites specifically. It contains substances that are toxic to these termites, and it attracts them to ingest it and take it back to the colonies. And when they take it back to the colonies, that lethal substance spreads throughout, eliminating termites, especially because termites in particular are cannibals. In the event that a termite is injured or cannot perform their colonial duties, they are eaten by other termites, thus spreading the lethal substance, making this particular method very, very effective. Another method commonly used to prevent subterranean termites is the use of metal shields for concrete footings. And this is a metal shield right here, and it extends past the profile of this footing. And what it does, it prevents subterranean termites from crawling up to accessing this wooden member. Another method commonly used are termiticides. Termiticides are very, very effective because they penetrate very deep within the timber members, eliminating those timber beetles that I mentioned earlier, where the larva burrows very deep within the timber, sometimes for 2 to 5 years. Most termiticides will eliminate those. However, it contains DDT, which is very bad for the environment. So there are lots of concerns about this method of prevention, and a lot of efforts are being taken to reduce the amount of DDT or using a combination of other methods. Another method commonly used before the construction of a structure is pressure treatment of the wood. Now, this method, it reduces the moisture content within the timber. Like mentioned before, especially with the timber beetles, they use the water in the timber to digest the protein that they need. So if there's less water in the timber, it becomes a less attractive environment for them to dwell in, making the probability of infestation from timber beetles less.
So now we are going to compare the environmental performance of concrete and timber from these 4 aspects. For the economic damage of the AAR, we cannot find a lot of information about it because actually AAR damaged the structure not directly. So it just reduced the strength of the concrete structure but not damage the whole structure. So that there is difficult to calculate the economic damage of AAR.
Likewise, it is also hard to find information on the economic damages of insects and bugs on timber members, just because there are so many insects and bugs that infest timber, a lot more so than just the termites and the timber beetles discussed earlier. However, it is estimated that termites alone can cause about $15 to $20 billion a year worldwide.
So for the speed of deterioration of AAR, as it is a very slow reaction, so that it takes about 2 years to reduce the strength of the concrete structure by half.
And the deterioration of timber member structures greatly varies depending on the different species of insect or bugs that are infesting the timber. These different variables include size of the colony and behavior of the insects or bugs. However, some size colonies and species can destroy residential houses within 1 to 2 years.
For the process of deterioration of AAR, it spreads from inside to the other side of the concrete structure, and it starts from the bottom.
Bugs and insects typically infest timber members from the bottom of the structure to the top of the structure, and as well as from inside the timber member to the outside of the timber member, except for in the event of termites, in which they infest both the inside and the outside.
For the prevention methods of AAR is to reduce the occurrence of this reaction by reducing the content of reactants, the silica, alkali content, and also the water content in the concrete.
As stated before, some of the methods most commonly used to prevent the infestation of insects and bugs are the baiting system, the design precautions like the metal sheets used in the construction of concrete footings, the application of termiticides, as well as the pressure treatment of the timber used for construction.
Next, we'll take a look at professional practices. As an introduction to professional practices, we already looked at thermal conductivity of the both materials that we were looking at. Thermal conductivity should be known for this material, whether it is the in situ timber that you're taking or the thermal conductivity of the concrete mix that you prepare. This is a very important property because if you use a material with too high of a thermal conductivity, you may end up paying a lot for costly installation or even reconstruction. Here in this table, there's a comparison of thermal conductivity of various materials. If you look at lightweight and dense concrete, you see a range from first of 0.1 to 0.3, and then from 1 to 1.8 respectively. Timber has a thermal conductivity of about 0.14, and this is in kilowatts. Yes, and you can also see the comparison against stainless steel, water, and Portland cement. So for some hands-on professional experience and practice, the group thought it would be nice to test some concrete and timber for the thermal conductivity. And according to this table, our hypothesis would be if we're using average concrete versus timber, then the thermal conductivity of the timber should be less than that of the concrete.
And now time for the methods portion. A sample is held under a compressive load between two metal surfaces. These different metal surfaces are at different controlled temperatures. The heat flux transducer is on the bottom surface, and that is calibrated. An axial temperature gradient is established in that stack as heat flows from the top surface down towards the bottom surface. The output from that heat flux transducer can determine the thermal conductivity of the sample when the thickness of the sample is known. Specifically in the DTC 300, a guard furnace surrounds the test stack as an isolation to reduce test error. In the DTC 25 test, it is conducted at room temperature and therefore does not require a guard furnace.
As we mentioned previously, the large-scale experiments should be replaced by the small-scale experiments due to these three limitations, including the lack of equipment, limited budget, and also lack of time. However, these three limitations need to be accurate in the small-scale experiments. For the lack of equipment, it's difficult for us to create a large temperature difference in different experimental settings. And this will lead to less obvious results in the small-scale experiments. And it's difficult for us to control or maintain a constant environment, as in the larger scale experiments, a large energy is involved in the experiments. So that if we use a smaller scale experiments, it's difficult for us to control the heat loss, so that the errors of the result will be larger. And second is a limited budget, as we need a lot of money to purchase different kinds of materials, and those materials are very expensive. And also we need a more accurate measure tools, like a more sensitive thermometer, so that if we doing the smaller scale experiments, the quality of material and also measure tools will be lower, so that the error will be larger. And thirdly is a lack of time. As the large scale experiments, it takes at least 3 days to complete. Although we can use shorter time to complete the smaller scale experiments, but the results will be have a larger error. So that due to these three limitations, it leads to a very large error, so that the result will be very inaccurate.
So to conclude, in terms of microstructural features, thermal properties, and environmental performance, concrete and timber are two very different things. And for both microstructural features and environmental performance, similarities probably cannot be found between concrete and timber. For microstructural features, timber and concrete are different in terms of the equipment used for examination, the density, the components, and the function of water. For the environmental performance, the two materials are different in terms of the economic cost, the time of destruction, the process of deterioration, and the nature of prevention. Actually, concrete and timber also perform differently in terms of thermal properties. For thermal properties, concrete takes the advantages However, timber takes the advantages on fire resistance. For both concrete and timber, the thermal resistance can be increased by using special designs or additional materials. In order to test the thermal conductivity of both concrete and timber, a simple professional practice is carried out. However, there were some limitations, and therefore it is not accurate enough for us to test the thermal conductivity of concrete and timber. Therefore, this experiment is not included in our project.